Yes, go for it.
Perfect. So my name is Daria, and I'm a head research scientist at Cerebras. I sort of wanted to give you a bit of a background about me. I've been working at Cerebras for 4 years, and before that, I was at Google, Analytics and Cisco. I've been always passionate about NLP and sort of like its applications at scale. So recently, I've been working on mixture of expert models. And I picked an example, which is like a DeepSeek model, the DeepSeek V3, that was recently released. And I sort of wanted to give you more details on what the model is and why it's more compute efficient than anything before it, and why it's so successful at quality. So here's like a rough diagram about the model itself. You don't have to actually understand everything here. Essentially, there are different improvements that the team developed, but I'm going to focus on one specific that kind of gave it a lot of boost, which is the mixture of expert side. So this model is the mixture of expert model. It's not an analytic structure. It's still transformer, like we all know, but it has different experts, and we're going to talk about like where exactly. One interesting bit about this model is it has the largest number of experts released on open source. It has 256 experts. And I'm going to explain like why that helps with the compute efficiency. So we can skip to the next one. Here is the benchmarks that this model was run on, and you can see that it's comparable to closed source models like Claude and GPT-4o. There's some other models, like you can see that they're beating the previous version, Command Llama, etc. But I think what's interesting about it, when I was looking at the benchmarks, the GPQA Diamond in particular, that's the data set that was created specifically to answer basically like PhD level questions in different domains. So you have biology, math questions that are really hard to answer, and PhD levels can only get to up to like 65% accuracy. And you can see here that the DeepSeek model is quite accurate on that benchmark. And also like on math and reasoning, obviously, it's also better. Next slide. I guess we can click through this one because it has animations. Yeah. To sort of like give you the trends in the community, what people are working on, we started with the GPT-3, which basically is a 175 billion model. It was released a few years ago. That was an analytic model. It was based on a transformer, and the high-level idea there is as you increase the model size, you always get better quality. So you have scaling laws where your larger models will basically have more skill set, or like will develop new skills and storing parameter counts. Then we had Llama 3, and those models, they essentially show that in addition to the model size, you need to scale your data, and you need to curate your data more. So there was a lot of effort that Llama team spent and creating the better data sets. And the last thing we did, DeepSeek V3, essentially the foundational model that they trained, it has a different architecture, so it's no longer an analytic model, the transformer based. It's still transformer based, but it has different branches, and it doesn't activate all of them. So this is kind of the trends in the community, and I'm gonna like explain to you why that all matters. So if you guys are familiar with like a transformer backbone, or like a decoder pod of the transformer, then here is a zoomed in version into like specific part of it, which is called feed-forward network. To like recap, there are 3 types of layers like that are important to talk about, usually embeddings, attention, and the fully connected layers, which is called feed-forward here. And they all have different tasks, they solve different problems. So we're going to talk about feed-forward in particular. From like interpretability perspective, feed-forward is the layer that has the toughest job across all of them. It has to kind of disentangle information and kind of like understand how to separate a particular neuron in a network that would get activated essentially when you see like a golden gate bridge in a text. So because of that, we want to kind of simplify the task for a feed-forward network. We want to create multiple feed-forward networks within one network. So you can see the diagram on the right. There are different experts, and each of them has its own feed-forward connections. Now, like the hope is each expert will specialize, let's say, in particular domain. So there will be a math expert, or there will be like a code expert, and altogether they will be better at solving a particular task. Also, to sort of like decide how to select a particular expert and the training time, there is additional network that's added. It's called router. Each router is basically like a classifier, and it classifies where a particular token should be routed to. That helps to like distribute the load across different experts. Next slide. I guess like this is probably the most interesting slide. We can click for all of it. So mixture of experts, essentially, it is still kind of aligned with the original methodology. We want to increase our model sizes as much as possible, so we want to go to 1 trillion scale and beyond that, because that gives better quality. So whatever, like the end user who will use the models, they will have better reasoning and better coding skills, etc. But if you go with the dense models, or like monolithic models, it's going to be very compute inefficient. You grow your parameter size, and as we heard on previous talks, that's very hard to run on GPUs, even on Cerebras hardware. So essentially, if you want to increase the model size to 1 trillion and beyond that, the most efficient way to do it is with mixture of experts. Essentially, as you increase number of experts, and DeepSeek had 256, you don't have to activate all of them. So the mixture of expert model released by DeepSeek is 600 billion in size, which is the largest monolith shared. Like Llama is 405B and GPT-3 is 175B. But it's only using 40 billion of those parameters at the inference time. So when you generate a token, it's only activated 40 billion parameters. It's much smaller, but it's much more, it has more accuracy, right, this model compared to the other models that I talked about. Now there is some caveats. Even though we are more flop efficient, they have way more number of parameters. So at the inference, when you have 600 billion parameters, you have to load all of them. You have to load all of your experts, because you don't know really where each particular token will be routed to. So that becomes inefficient from the storage perspective compared to dense models. So let's see here, like the dense model has let's say 1x number of parameters, but with average number of experts, 16 to 32, you will have 4 to 8x increase in memory, which is a lot. Now, maybe you're asking what are the tricks to still maintain the same quality as the mixture of expert model, but maybe be more efficient at inference as of today? There are certain techniques like distillation. So DeepSeek released a few variants that they distill their mixture of expert models in dense models, so you can run that. It's going to be more parameter efficient. There are also techniques where there are a lot of studies basically that people try to figure out you actually need that many experts. And I showed you just one layer of transformers. You have 256 experts at one layer, but transformers are deep. So you have 10 layers, multiply number of layers or number of experts. This is how many you have. And there might be some redundancy in it. So there are techniques and kind of research directions that we're also exploring, where you try to merge experts that perform very similar transformations and sort of redundantly separate experts. And that can shrink the model size, because instead of 256, you can end up with 128, let's say. Some other techniques like quantization, and this was used in a DeepSeek paper. Instead of FP16, they used FP8, so you can quantize your weights and use lower precision and still maintain the same level of quantity. I guess that kind of concludes my talk. Are there any questions?
So you mentioned the inefficiency will lie in the redundancy of experts and let's just stay there, the redundancy of experts. Do you happen to have any personal thoughts or opinions on where other potential inefficiencies might lie?
Yeah. So I'm happy to talk about it in more details afterwards as well, because I'm very passionate about the directions in particular. But so one thing is, first of all, when you increase the number of experts, the standard technique would be to just copy paste each expert and grow them identically. You have experts that have the same number of parameters. That turns out to be inefficient because As you increase the number of experts, there are more and more redundancy in it. So there are techniques on how to, let's say, shrink each expert in size. As you grow number of experts, you make each expert smaller. There are scaling laws produced by a bunch of different people showing that benefits. I also believe in that. But maybe I'm trying to think going forward. Right now we have techniques that basically tell you how to shrink each expert, but sort of uniformly across layers. But I believe that the kind of autoencoder type of architecture, there are different types of features that you learn in the middle of the autoencoder and towards the end and in the beginning. So decoder from the transformer is very similar in that. And I believe that there are different types of features that you learn in different layers. So you might shrink your experts differently at different layers. And yeah, that's, I think, very exciting direction. So if we're gonna continue growing the models in size, we care about whether each expert is actually adding any new functionality to the existing experts, and if it doesn't, we should penalize it for it, and that could be through shrinking each expert in size.
Thank you.
Anyone else?
Can you talk a little bit about hard versus soft routing and how that might affect efficiency?
So could you clarify what exactly?
Sure, yeah. So say for example, combining a bunch of outputs from a bunch of different experts versus selecting some subset of experts and just looking at their outputs. So basically weighting what the experts say versus just routing it to one specific expert.
Whether what's the software issues or hardware issues with that approach?
No. So I guess soft routing, I think is when.
Soft routing.
Yeah.
Okay.
Yeah. Soft routing versus hard routing.
Oh, I see. Okay. So there are different types of hard routing. There could be hash functions that you can use, a token ID, % number of experts, let's say. So they tend to help a lot with the stability of training because you don't have the router, and the router as a network, it has to learn where to route stuff, right? But it doesn't seem like that affects quality as much as the soft routing would do it. So when you have a learned router, it's always better than the hard coded router. But one thing is to answer maybe the previous question as well, we kind of hope that as we add more experts, they will become more specialized, let's say, in something, right? It doesn't really happen in reality. What you have is almost a monolithic structure in a lot of different layers, where you activate one expert and it gets the majority of the tokens, everything else stays idle. In that sense, hard-coded routing would be better because it would allow you to load balance. It will allow you to use all of the different experts. And there are techniques to show let's just do clustering on your data set and figure out the clusters and assign each token to a particular cluster, and then each expert will only be trained on the data from a given cluster. That can improve specialization and also utilization of your experts at different layers. But it seems like it's still less compute efficient compared to direct routing.
So I guess I follow up on that. How do you identify how many experts to have, or in other words, which experts you should have? So for example, say you're looking at a data set of every single object in the world, there's infinite different ways that you can cluster that in different subcategories. Do you just run some basic data analysis on percentage distribution across each of these different categories, and then use the same ratios to train the same different models? Do you use clustering based approaches, find the top K different clusters, and then create K different experts? What do you actually do?
Yeah, so there are a lot of different ways to do it, and you mentioned some very practical ones. I am a firm believer that we should work with learned routing, which doesn't really cluster anything beforehand, but there are certain techniques that we try to add to the router itself, so we can try to at least get some feedback from the model to actually cluster something. Let's say, I don't want to have giant expert in one particular layer, but the router doesn't really know anything about it. So you can add some penalization to the network that would allow for the same kind of effect that the hard-coded routing has, but you still have the benefits of context learning that the router, the learned router gives you.
On the topic of routing and load balancing, the DeepSeek V3 paper makes stared at that a lot, and I just don't understand why it's that different and why it should be something that changes the behavior a lot.
That's a very good question. So the load balancing issue that we have in mixture of experts has been studied. Like it has been studied back to the 1960s. There are a lot of different techniques that work for it. So there is like synchron routing that was created in the 20th century, and it doesn't even have any gradient propagation, but it allows you to load balance across different experts. So there are a bunch of papers that actually use that instead of like switch routing, which is what I guess like DeepSeek also kind of adopted. And to me, like there are a lot of different techniques to deal with load balancing. They chose one that worked for them, but it's not a hard problem to solve. One thing that they mention is you add load balancing loss into the cross entropy that somehow hurts performance. I do believe in that because basically you have a combination of two losses to optimize, so you are worse than cross entropy. But in my experiments, kind of like forcing load balancing doesn't really affect the quality. But that probably means that our routers are not can have some space basically to improve.
And I guess that is like loosely what they're, like rather than including in the loss, they just adjust the bias on each expert after each batch so that it would have led to an even distribution, which is closer to like hard coding load balancing rather than incorporating the loss.
Exactly, yeah. So like there are a bunch of other works. There was a Skywork MOE that was released I think a few months ago. It kind of did some other heuristics to basically like penalize particular expert that kind of exceeded the given load. I guess like all of them are trying to do that just for the hardware perspective. It doesn't seem like that improves the quality of the model. So what I can like say, let's say, I actually presented at yours, so I can say about it. There is a switch routing that's lower routing, right? And it could do like a very bad job in terms of load balancing, and it can have like a very large expert at a given layer. Synchron, essentially the same level quality, but it would take the distribution that was created for switch and it can just redistribute the mass because it has like a dual objective. It tries to improve like the mapping between a token and expert, but also tries to load balance. So you can load balance perfectly, but it doesn't improve the quality. The reasons why is because you just like almost uniformly distribute the mass of like, you have one giant expert, you can like distribute it between two experts. They perform the same transformations, the model doesn't really care. So your experts in a way like perform the same transformations. That's kind of like the problem in all the mixture of expert models. And load balancing does really help with that. Sorry for a lengthy answer. Yeah.
Sorry, it came late, but and maybe you've already answered this, but do you see a trend on like whether the sparsity of these MOEs, like the active to total experts, do you see that growing because of these balancing and routing challenges, or staying roughly the same, or is that a scalable direction?
I guess like you're asking whether that's a scalable direction to increase the number of experts?
I would like total ratio of active to total experts. So like right now DeepSeek has 32 of total to active, like 8 out of 256.
Yeah.
What if you wanted to do 8 out of 512? Would that work? What happens when you make it really sparse?
It's a very good question. So because of the issues we have with the router right now, I do think that you are more aggressively activating more experts as you increase number of experts. Because essentially, like, as I was telling, like, if we activate just one expert per given token, you have like this mode collapse issue where one giant expert is being used, everything else is not being used. When you activate more experts per token, the issue is a bit better. So there, I would say like the rate at which you increase the number of active experts with state-of-the-art routing is slower compared to how you grow your number of experts. Because we also don't want to be flop inefficient, right? If you activate everything, we're going to be as bad as dense model with giant number of parameters. So there's scaling laws that basically tell you like how fast you should grow your top K compared to number of experts. And yeah, like I think probably my intuition is as we fix the router, there's a lot of work that kind of tries to It's like change the router, change the way that experts transform its inputs, then we won't need to activate as many. So like the original switch transformer paper kind of said that you only need one active expert per token. I do think that maybe at some point, like when the router is fixed and the experts actually specialized, then we will be slow. We will grow like top key slower compared to what we have right now.
So you think that the experts per token will also need to grow?
You believe that experts per token will also need to grow with the total number of experts, but slower?
You mean the total, the active number of experts? Yeah, I mean, there's some prior work, and DeepSeek also used that. The paper is called fine-grained MOE. Essentially, it showed to you that as you increase the number of total experts, you want to make each expert smaller in size, but to stay isoflop, you also want to activate more experts per given token. So there is like a formula from that paper that tells you like at this given like number of experts, you want to activate that much, and you're going to be compute efficient. Because as you, it's a fine-grained mixture of experts. University of Warsaw published that.
Any other questions?
Yeah, so I was like looking up, like, I think there's some formula in the DeepSeek MOE paper. It's something like the number of times each expert selects something times the expert's average score over the sequence. They have some sort of like sequence-wise loss thing. Have you guys explored any better ways to do loss than that, or like, what are your thoughts there?
The load balancing loss?
Yeah.
Yeah, so there is an algorithm called SynCore. It's essentially, it's a credit-free algorithm, and it has a dual optimization objective. So it's like iterative algorithm, right? And essentially, it has like iterative algorithms separately created for each layer. And there is a paper called Mamba, I think, Mamba by Luther. So they use synchron routing, and they showed how great it is at load balancing. You don't need to have a load balancing loss. And it's actually implemented like as a iterative algorithm for like a couple of iterations. It doesn't have, like it converges pretty fast, but it maintains almost perfect balancing within each layer, which is a big problem if you have like load balancing loss, no matter sequence, batch size, whatever. You have to sort of like aggregate it across layers because you need to add it to the loss, which is the final thing, right? And usually when you like control an average or whatever other like aggregation you do, you don't really control each layer, right? You kind of control an average, which makes some layers very like inefficient because you have like giant expert that's been used and nothing else being used, but other layers are sort of okay, so on average you're kind of okay. But to me, like controlling load balancing through load balancing loss is not very efficient. There are other methods to do it. I mean, synchron is kind of hard to implement, I guess, but I refer you to like a Mamba paper because I made it work by looking at that.
Any other questions? Okay, thank you so much, Daria. Thank you to all our speakers tonight for the programming. I think right now